Well, in section 3.2, we've been searching for a set that might have a larger cardinality than the set of natural numbers. So let's just review for a second what sets we have talked about. We know that the real numbers contain the rational numbers, which we call Q, the rationals, and those contain the integers. I'll call those I for now. And then those contain the natural numbers. So the natural numbers are just the counting numbers written here. The integers are all the positive and negative ones, including 0. That's the set 0. Well, let me do it this way. Minus ... minus 3, minus 2, minus 1, 0, 1, 2, 3, ... That's our integers, the negative and positive whole numbers. Q is the set of all fractions. I'll just write fractions. And R is the set of real numbers, all decimal numbers, irrational and rational. So we have, and I'll show you in just a second, how we have already shown that even though the integers contain infinitely many numbers that are not in the natural numbers, all the negative numbers, they have the same cardinality. The set is really no bigger. And what we're going to do in this video is to look at the set of all fractions, all rational numbers, and see if that set can be put into one-to-one correspondence with the set of natural numbers. Let's review for a second how we decide if a set has the same cardinality as the set of natural numbers. We said that an infinite set that can be listed, put on a list, has the same cardinality as n. For example, the integers. I just showed you that we could write them this way, ... minus 3, minus 2, minus 1, 0, 1, 2, 3, ... That's the set of integers. Call them capital I if you want. And there I have put them in order. And notice it is not a list because it goes infinitely to the left and right direction. A list has a first, a second, a third, a fourth, etc. But these are easy to list, and we did it in class. 0, and then we could just toggle. We could say 1 minus 1, 2 minus 2, 3 minus 3, and so on. And everyone can see, yes, all of the integers are on that list, and each one only once. By the fact that we can list them this way, we know that they are in one-to-one correspondence with the natural numbers. Now, how does listing guarantee that? Well, let me choose a different color here, and let me write underneath these numbers 1, 2, 3, 4, 5, 6, 7, ... The correspondence is 0 with 1, 1 with 2, -1 with 3, 2 with 4, and you see this natural correspondence set up by the list itself. And when we ask what is the correspondence, well, we say that each number on the list corresponds to its position on the list. In other words, said in a more mathematical way, we could say the nth number on list corresponds to the number n. Each number on the list corresponds to its position, and that is a one-to-one correspondence, as long as no number appears twice on the list. Naturally, the next set, which contains many numbers that are not integers, not natural numbers, is the set of all fractions, the set of rational numbers. So now we want to ask, can we put them on a list? We certainly know that we cannot list them in order because there is no rational number next to the number 1/2. There's always more rational numbers between any two that you pick. So this will be a much harder task to try to list them, but let's see if we can. Before we start, we need to make sure that you understand these words. A rational number. A rational number is a fraction a over b, where a and b are integers. And of course the denominator can't be 0, so I'll put b not 0. That's a rational number, a fraction. Now a proper fraction, we're going to need that word in making this list. A proper fraction is when the numerator is less than the denominator. For example, 2/3 or 100 over 203. Those are both proper fractions. And it turns out if the number is a proper fraction, it is less than 1 because the numerator is smaller than the denominator. And the reciprocal of a over b is, well, in section 2 we were really we were looking for patterns, so we said it's 1 over a over b, but in this section we'll be more interested in the simplified version of that. It's simply b over a. So the reciprocal of a over b is b over a, and the only number that doesn't have a reciprocal is 0. Making a list of the rational numbers using this method, there are many, using this method we will use 4 stages. It's a different method than used in the book, but it is one that one of the authors taught me how to do. So, stage 1. Stage 1 in making our list of the rational numbers is we're just going to put the natural numbers on the list because every natural number is a rational number. So I'm going to start with just putting 1, 2, 3, 4, 5, 6, and so on. Now, I would make a big space in between those in actuality because I'm going to be inserting many, many numbers in between these two. But the first ones I put on the list are just the natural numbers. Okay, now for stage 2, notice I did stage 1 in blue. I'm going to put in yellow numbers in stage 2. And notice also here that I have separated out the 1, 2, 3, 4, 5, 6, ... I've made big spaces between the natural numbers because I'm going to have a method of inserting numbers in between them so that I can get all the rationals on the list. Okay, so stage 2 is insert the proper fractions. Insert the proper fractions, numerator less than denominator. Insert the proper fractions with the denominator n right before the natural number n. Only put reduced fractions onto the list. We don't want to put 2/4 and 1/2 by accident on the list, or our correspondence would not be 1-to-1. So let's just agree that we only put reduced fractions on the list, and then we can be sure that we won't duplicate one. So let's see, right before 2 I want to put in 1/2. Before 3 I want to put 1/3 and 2/3. Before 4 I want to put 1/4. I'm not going to put 2/4 because we already have it, it's 1/2, only in reduced form. So I don't put 2/4, but I will write 3/4. And before 5, well, before 5, 1/5 is a prime, so 1/5 and 2/5 and 3/5 and 4/5 all go on the list. All the proper fractions that are in reduced form with denominator 5. Now before 6 I'm going to put 1/6, not 2/6 because 1/3 is already there. 3/6 is 1/2, it's already there. 4/6 is 2/3, it's already there. The lower denominators have already been done, so only 5/6 will be put on in stage 2, and so on. We keep going. So now here we are at stage 3. We have all the positive proper fractions on our list, and we have all the natural numbers on our list. Well, now I'd like to, in the next stage, put all the positive reciprocals on the list. So we'll get all the fractions greater than 1, essentially. So let's insert to the right of each number. We just agree on that. There's no reason why you couldn't do it on the left, but we're going to agree. We need a method to making the list. So to the right of each number on the list, let's put its reciprocal. Only if that reciprocal is not already on the list. Remember, if we put, well, I'll tell you as we go along. Let's do this in red. And the reciprocal of 1 is 1. I don't need it. The reciprocal of 1/2 is 2. It's already there. The reciprocal of 2 is 1/2. Nope. The reciprocal of 3 I have. The reciprocal of 2/3 is 3/2. It's not on the list. 3. I already have 1/3. If I were to put 1/3 here, it would be on the list twice. So it would correspond, 1/3 would correspond to two different natural numbers, two different positions on the list. The correspondence would not be 1-to-1. I don't need 4. 4/3, I'll do. 1/4, we don't need. 5, we don't need. 5/2 is not on the list, so on it goes. 5/3, we need. 5/4 is not on the list. 1/5 is. 6 is on the list. 5/6, well, 6/5 is not on the list. And 1/6 is on the list, and so on. So I hope you see, this list, I'm just showing you enough of the list so that you can understand how the entire list is made. It's important to see at this stage that we have now all positive rational numbers on the list. First we put on the natural numbers, then we put on all of the proper fractions, and then we flipped all those over and put on all the fractions greater than 1. So at this stage I think we'll do a couple of little exercises to make sure that you see at this point all positive rational numbers are on the list, certainly not in order. So we're stopping for a second at stage 3. It'll be easy to put the negative numbers on. We'll just insert each one next to the positive. So do we have all positive rationals? Well, I claim that we do. And so just to make sure that you see, let's do a couple of little exercises, and you'll have more of these to do in class. Where is, for example, the number 0.12121212 repeating? Well, we know it's rational, don't we? It's a repeating decimal. So it is rational, and it has to be on the list. Well, this list is made using fractions, so we have to change this number into a fraction. So let me call it something. Let me give it a name. I'll call it n. And you remember the way that we did this is, well, I like to look at the repeating part, and so I have to multiply that by 100 to move the decimal point past the first repeating part. So 100n would be equal to 12.1212 repeating, and n itself is equal to notice lining up the decimal points, repeating. And so then our technique was in chapter 2 we subtract, and we get 99n is equal to 12. And so n is equal to 12 over 99. It says which stage was this number put on? Well, remember, numbers were put on in reduced form only. This is a proper fraction, so it's definitely going to be in stage 2 after the natural numbers, but let's figure out exactly where it was put on the list. It wasn't between 98 and 99, because if we reduce this and divide by 3, we get 4 over 33, which is reduced. So this number was put on the list in stage 2, and it was between, we put it between 32 and 33. Those were put on in stage 1, all of the natural numbers. Here's another question similar to the last one. When was 41.2222 repeating? Well, again, we can't tell because this is in decimal form, so we need to change it into its reduced fraction. Clearly it's bigger than 1 and it's positive, so it will be in stage 3. But let's figure out where it went exactly. So if we give this one a name, let's call it M. Then circle the first repeating part, and I just need to multiply M by 10 to move the decimal point past the first repeating block of digits, and then subtract M, which is 41.2222 repeating, and subtracting, I get 9M is equal to, subtracting, of course, all of this goes. That's why the technique works. 1 from 2 is 1, and 371. So M is equal to 371 over 9. Now the only prime that goes into 9 is 3, and 3 does not divide 371, so this number is reduced. It's greater than 1. It's not proper, so we know it went in stage 3, and it went in right after the number 9 over 371. Remember, we flipped it and we took 371 over 9, so in stage 3 that's what that looked like. And so this number, if you were asked between what two natural numbers did it go, it was between 370 and 371. 9 over 371 was put in there, and then in stage 3 it was flipped over. So here is stage 4. I guess I used red again. I typed this out on my PowerPoint slides, so sorry I repeated a color here, but stage 4 here is shown in red. And all I'm doing at this point is we had all of the positive rationals. All we need is 0 and the negatives. So after each number I inserted its additive inverse. I inserted its negative. After 1/2, minus 1/2. After 2, minus 2. And this is the list of all of the rational numbers Q. That is all of it. So we have shown that we can make a list of all of the rational numbers. And just to review one more time, by showing a method of listing the rational numbers, what have we proven about that set of numbers? Well, we made a one-to-one correspondence with the natural numbers. So we have shown this. The rational numbers, I should say the set of rational numbers, has the same cardinality as n, our set of natural numbers. That's pretty surprising, really. Maybe infinity is just infinity. Maybe there is no set bigger than n. Although the rational numbers contains infinitely many numbers that are not in n, it still is not a larger cardinality. We can still make a one-to-one correspondence. So I hear students all the time just say infinity is infinity. So maybe you're right. We'll have to go on to our last hope, and that will be the set of real numbers, and we will see if the real numbers can be listed.